Hi, my name is Emily Tom, and I am a first-year material science and engineering grad student at Michigan Technological University, and I will be presenting on the investigation of novel magnesium, zinc, calcium alloys for bioresorbable orthopedic implants. So an orthopedic implant is used to help align a bone when the bone cannot readily heal on its own and is a permanent fixture in the body. But we are trying to develop a bioresorbable implant, which will essentially corrode, as you can see in this picture on the right, as the fractured bone heals, allowing the bone to take over the mechanical strength that the implant would otherwise hold. And so these bioresorbable orthopedic implants offer a reduced chance of secondary surgery to fix complications with the implant, a reduced chance of late onset pain from the implant, and a reduced risk of infection. And so all of these would benefit a long-term space travel application for fracture fixation of broken bones. So we have chosen magnesium, zinc, calcium alloys because they have a great biocompatibility and a strength similar to that of bone, but they corrode too fast in a bodily system to maintain the mechanical integrity that is needed for bioresorbable orthopedic implants. So as you can see here, they corrode too fast because of the presence of coarse precipitates that are formed when zinc and calcium are added to a matrix or magnesium matrix. And since they have a higher electrochemical potential, they will corrode preferentially, causing localized pitting and cracks, as you can see here in these two micrographs, that will compromise the mechanical integrity of the bioresorbable implants, causing them to fail earlier than the bone has healed. So we are looking to combine two non-equilibrium processing techniques, rapid solidification and equal channel angular pressing, or ECAP for short, to improve the corrosion and mechanical properties of magnesium, zinc, calcium alloys for bioresorbable implants. So as you can see here, rapid solidification of a magnesium, zinc, calcium alloy greatly improved the corrosion resistance and corrosion behavior of the alloy, where you can see that there's no localized pitting or cracking. And this is due to the rapid solidification process trapping atoms within the solution instead of allowing them to precipitate out, eliminating the presence of these precipitates. And then ECAP processing greatly improves the ductility of the magnesium alloys, as well as improving the mechanical strength through allowing the alloy to dynamically recrystallize during processing, which eliminates the presence of very big precipitates by essentially crushing them up into smaller granules, as well as reducing the grain size, which reduces the amount of stress in the microstructure. So I will be developing two magnesium, zinc, calcium alloys with trace amounts of manganese to evaluate the mechanical properties and corrosion behavior of these alloys after they have gone through the melt spinning process, which will produce magnesium, zinc, calcium ribbons. And then these ribbons will be consolidated through hot extrusion. And then after extrusion will be subjected to ECAP processing, as seen here in this picture on the right, to develop an alloy with a reduced number of precipitates and smaller grain size, which will aid in corrosion behavior and mechanical strength and ductility increases. And so thank you for coming to this talk.